another aspect of amplifier design, which is the efficiency aspect. We all know that we want transistor in our amplifier to be highly efficient. We want that the total power consumed by the transistor is very less. So, for but then if we reduce the power, then we have to compensate on something. If we want the input and output voltage relationships to remain perfectly same, that is the input voltage. If the input voltage is a perfect sinusoid, then the output voltage should also be a perfect sinusoid. If we want to ensure that, and at the same time we want a higher efficiency, then we have to compensate, we have to cut corners on the output current. So, that is how we can, so by reducing or compromising on the quality of the current output, we can ensure that the efficiency of the amplifier is high, and however the voltage waveforms remain the same. So, depending on this, a certain classes of amplifiers have been formed. So, here if the transistor, assuming that we have only a single transistor in an amplifier, a transistor, the characteristics of the transistor that we use for this analysis is what we call the ideal transistor characteristics. So, this is a MOSFET whose drain current versus gate source voltage relationship is like this, and whose drain current versus VDS, that is drain source. So, this is the previous one is the gate source voltage on the x axis, on this one has VDS or the drain source voltage along the x axis. And as we know, the characteristics can be divided into two minimum regions, the triode or the linear region and the saturation region. Now, depending on what angle, or for what angle of a sinusoid the transistor is conducting, that is for what angle values of the input sinusoid, or for what phase values of the input sinusoid our VGS is above the threshold voltage, we can classify our amplifier into class A, class AB and class B and class C. So, 4 classes we can achieve. So, if our transistor is conducting for the entire 360 degree phase variation, then it is called a class A amplifier. If it is conducting for phase between 180 degree and 360 degree, then it is called a class AB. If it is conducting for exactly 180 degree phase angle, then it is called a class B, and if it is conducting for less than 180 degree, then it is called a class C. So, this is how we can classify. Now, low noise amplifiers, because they need to provide high purity in the input signal. So, here we cannot compromise on the current, that is why low noise amplifiers excuse me, they usually operate in the class A region. Power amplifiers on the other hand, where signal purity is not so critical, they have a wide range of classes from A to F. Now, beyond class C, that is the class D, class E and class F are called switching amplifiers, and they are a separate category. They don't, the conduction angle is not a factor there. So, let us see a class A a simple class A amplifier, how it can be built. This is a class A amplifier with a, this is our MOSFET with a load RD. Now, the operation of this class A amplifier is like this. First of all, note that because it is operating for the entire region, that is the transistor is always on, our input will have to be in that region of the ID versus VGS characteristics, where the entire 360 degree can be accommodated. So, if our input amplitude is very high and suppose the negative part goes beyond this Vp somewhere around here, then it is not a class A amplifier. So, it is conducting for the entire 360 degrees, and similarly this is the input voltage, and our ID also is a perfect sinusoid. It conducts because VGS is always on, our ID will also provide an output which follows the input voltage. And finally, since our ID is a sinusoid, our RL will be ID multiplied by will be IL multiplied by RL, and so that is why we get our VDS is simply also a sinusoid like this, and our this is basically our output voltage, which is also a perfect sinusoid. So, this is the class A operation. Let us see what happens in class B. In class B, instead of just an RL, we now have a resonator with a resonant frequency of F0 connected in shunt with the load RL. Now, remember that this choke ensures that the total DC current consumed from the source Vd dd is constant. For the class B, as I said, it conducts for exactly 180 degree. Therefore, my input is now like this. See, only the half cycle, only during this half cycle, the input lies in the conducting region of the transistor. Now, because it is now conducting only for half cycle, note how ID changes. ID is now like this, a single half cycle, and then it stops. But what about my VDS? VDS on the other hand continues to be a sinusoid. There is no change in my output voltage characteristics. My output current characteristics changes. Recall that this half cycle is missing from ID, but VDS continues to be a sinusoid just like before. And finally, coming to class C operation, where the circuit is also exactly the same. Here the only difference is that instead of this being fed for the half cycle, it is now being fed for less than half cycle. VDS continues to remain a sinusoid, and my ID, because my input voltage, because my transistor is conducting for less than half cycle or less than 180 degrees, the ID is also conducting for a time, for a period which is less than 180 degrees. So, this is how the working of this transistor happens. Here of course, note that my input and output voltage characteristics are remain the same. They are of course inverted. When V input is rising, V output is decreasing. But when we say, sometimes it becomes confusing that whether the transistor is conducting class AB, when I say that the voltage waveform is that when I say that the transistor is conducting for class B, I say that the transistor is conducting for 180 degrees. It appears as if the output voltage will also conduct for 180 degrees. No, that is not the case. The output voltage will keep on remaining the same. It is just that the output current changes. So, so those are a few concepts that we introduced here. First was this bias, how to bias a circuit, then how to operate a transistor, how to design a transistor for it to be operating in the various class A, class AB and class B regions, so that we get better efficiency in our circuit. The next item I would like to cover is the aspect of frequency compensation. So, we know that, as I was saying before, that we designed our circuit at a particular frequency, but suppose we want to keep the gain constant. So, one simple way to do that, suppose we have at say a particular frequency f1 gain like this. So, this is my gain, this is frequency. At a different frequency I have this as the gain. So, how can I keep my gains constant? One way is to simply use a filter, okay, with a very broad band and bring this gain down so that it matches with the gain of this one at this frequency. This way we are compensating, forcefully making the gain same over the entire range. Or so to do this, what can we do? So we have a higher gain at a different frequency. So we don't want to reduce the gain here, but we want to reduce the gain here. So if we choose a filter with a characteristics like this, what will happen is, because the gain is lower here, this gain, the inherent gain at a particular frequency will be brought down, while the gain at other frequency where we don't want it to be attenuated will continue remaining the same. Some things we can do to improve the gain, or rather I should say the matching. So one method that is frequently used is what is called a balanced amplifier. If we go to the slides on the monitor, a balanced amplifier consists of two couplers, hybrid couplers or 90-degree couplers. Recall we have covered couplers previously, and two identical amplifiers. Any signal that is inputted at port 1 double dash, it will travel to both the inputs, both the amplifiers. However, the reflected waves will come back only at port 2 double dash. This we had already discussed, while discussing the applications of couplers, we had covered this topic earlier. So the purpose of the balanced amplifier, you see, is that since for a very wide range of frequencies, the reflected waves will end up only at port 2 double dash, hence we can achieve a very broadband impedance matching. The output impedance also can be matched over a very broad band by similar logic. Now another kind of realization of a balanced amplifier is this. Now here what you have is a power divider. Recall we have covered power divider, two identical power dividers, two identical delay lines and two identical amplifiers. It can be shown that the total input S11 here, that is the total input reflection coefficient and output reflection coefficient will always be 0. Not, when I say always, you might be thinking I mean infinite bandwidth, but it's not infinite, but a very broad band kind of, provided of course we have perfect matching between the amplifiers, perfect matching between the power dividers and perfect matching between the delay lines. And you can also be shown that the total gain of this amplifier is equal to the S21 square, or the gain of any of these amplifiers, any one of the two identical amplifiers. Now, in both this balanced amplifier, what is happening, as I said, all the reflected waves are get added up at port 2 dash. So, there is a load, matched load connected at this port 2 double dash, where kind of where the reflected powers are synced or wasted away. Now, similarly, in this amplifier, the other amplifier that we are talking about, this amplifier, what happens is that here also reflections take place, but instead of coming back to the port 1 or port 2, they are kind of synced or wasted away in these in this resistance that is present in the power divider. So, in this module we covered a number of topics, especially on frequency compensation, DC bias, and also power and also broadband impedance matching as well as broadband gain matching. There are some other aspects like associated with amplifier design, like linearity and power combination. So, that we will be covering in the next modules. Thank you.